Hi folks, today we're going to talk about arcs and chords. So this is the second lesson in our circles unit, and the last lesson focused very heavily on terms and being able to use them correctly to describe what's happening in or outside or on a circle. Today we're also going to start out with some terms and introduce some new definitions. So the first thing we want to talk about is something called a central angle. A central angle is exactly what it sounds like. It's an angle in the center. So the formal definition is an angle whose vertex is the center of a circle. And so that corresponds to this figure right here. Let's call this circle circle A, with the center at point A. And the central angle you see is right here. And we call it a central angle because its vertex is the center of a circle. And so we'll just say angle A. That's your central angle. The next word we want to talk about is an arc. And arc is an unbroken part of a circle consisting of 2 points called the endpoints and all the points on the circle between them. And so that corresponds to this figure right here. We have endpoints R and S and the points between them here. And all together, those things create an arc. And we call this arc, RS. You might notice some similar language in this definition because it kind of resembles the definition of a segment. The segment is part of a line. It's an unbroken part of a line consisting of 2 points called endpoints and all the points on the line between them. And so an arc is to a circle what a line segment is to a line. It's a portion of the bigger thing, but it does include the endpoints and all the points that are in between. So those two words should help carry us through at least the first page of our notes today. Now we're going to talk about different kinds of arcs. The first arc we're going to discuss is called a minor arc. Minor arc. A minor arc is an arc whose points are on or in the interior of a central angle. So we talked before about how a central angle is an angle with the vertex at the center of a circle. So here we have angle ABC as the central angle. But the arc, the minor arc, is the arc whose points are on or in the interior of the central angle. So point A on the central angle, point C on the central angle, and all of the points in between in the central angle. So that is arc AC. That's your minor arc. And one of the things we need to discuss is the measure of a minor arc. The measure of a minor arc is equal to the measure of its central angle. Angles are measured in degrees, therefore arcs are also measured in degrees. So if the measure of this minor arc AC is equal to the measure of its central angle, then I would say the measure of angle B is equal to the measure of arc AC. That is a true statement. Now we have minor arcs and we also have major arcs, just like in music. Minor and major. A major arc is an arc whose points are on or in the exterior of a central angle. So again, we have our central angle here, angle B, and all of the points that are inside, including the end points, point A and point C, that's my minor arc. But the major arc is the arc whose points are on or in the exterior of the central angle. So it's not anything that's in here. All of that stuff, it's not there. It's all the stuff that's outside. So let me erase this. It's all the stuff that's outside. So on the central angle or in the exterior of the central angle. So all the stuff that is outside here. So this arc is not called arc AC because if we call it arc AC, then that kind of doesn't tell us if we're talking about this or if we're talking about this, and we need to know which part of the circle we're discussing. So we don't use AC to name this arc. We use ADC to name this arc. using 3 points ensures that we know we're talking about this major arc. And the measure of a major arc is going to be equal to 360 degrees minus the measure of its central angle, because 360 degrees is the measure in degrees of the entire circle, and if we just subtract out of it the measure of the central angle, and therefore the measure of the minor arc, then we're going to get what's left over, and that would be the measure of the major arc. So, the measure of arc ADC equals 360 degrees minus, let me see if I'm on the page, yeah, minus the measure of arc AC. We could also say that the measure of the major arc is equal to 360 degrees minus the measure of angle B, because these two measures are equal. Okay, and the last special arc that we talk about is a semicircle, something that you're probably familiar with, but we need to discuss the official definition. It says, if the endpoints of an arc lie on the diameter, so the endpoints are on the actual diameter, then the arc is called a semicircle. So here, this arc has endpoints E and G. So all of this right here is an arc with endpoints E and G at the end of a diameter, and so we say that this is a semicircle. Now we also have a semicircle here. So each circle is made up of 2 semicircles per 1 diameter. Now the measure of a semicircle is equal to 180 degrees. So let's talk about why. Well, the most obvious reason is that it's taking up half of a circle, and half of a full circle measures 360 degrees. Sorry, I'm second guessing myself this afternoon. The other way that we can tell that the measure of a semicircle is equal to 180 degrees is by looking at that minor arc measurement information. The measure of a minor arc is equal to the measure of the central angle, the angle with the vertex at the center of the circle. So if you look at the semicircle, here's my center. Maybe we call this center B, just like in the other ones. And this is creating a straight angle, but it's a central angle because its vertex is at the center of the circle. So this 180 degree angle also gives the measure of the semicircle, and that would also be 180 degrees. So if my central angle is 180 degrees, then my arc measures 180 degrees, and it's called a semicircle. Now, as you're writing these minor arcs and major arcs by name, minor arcs may be named by 2 or more points. So like we had arc AC here. But major arcs and semicircles must be named by 3 points. And the reason is because you have to be able to distinguish which arc you're talking about. Again, if you called this arc right here arc AC, I wouldn't know its difference from this arc AC. But as soon as you put point D in there, arc ADC, I know you're talking about the major arc. Same thing here. If you just call this semicircle arc EG, I don't know if you're talking about arc EG here or arc EG here. But if you include that third point, arc EFG, then I know you're talking about the top semicircle and not the bottom semicircle. So you need to be able to distinguish between the arcs that you're talking about and the arc that's kind of left over. So in example 1, it says, the circle graph shows the types of music sold during 1 week at a music store. So these depict music sales. In the circle graph, we're measuring by percents. So think about the entire circle. If the entire circle is added up, how many percent will the entire circle be? Well, all the way around, all the pieces should total 100%, right? That's all of the music sales. But think about in degrees. If we think about a circle in degrees, because that's what arcs are measured in, then that circle in degrees would be 360 degrees. So if I'm asked to find the measure of arc BC, I better be giving my answer in degrees. But what I'm given in my problem is all percents. So I'm going to have to convert percents to degrees. And let's talk about how you do that. If I'm finding the measure of arc BC, let's go find points B and C. Here they are. And then the arc is points B and C and all the points in between. So there is arc BC. Notice that arc BC is right where the wrap wedge is. And wrap makes up for 13% of the music sales at the store. So I need to convert 13% to an amount of degrees in that circle. So if I'm going to do that, I'm going to create a proportion. My first ratio in the proportion will all be about percents. So 13% for my arc over the total percent in the circle, 100%. And that should equal whatever the measure of arc BC is in degrees over the total number of degrees in a circle, which is 360. So you might recognize the language part over whole equals part over whole. I'm trying to figure out this part in degrees instead of a percent. Okay? So in order to calculate my missing value in my proportion, I'd cross multiply. So 100 times the measure of arc BC equals 13 times 360. Notice how I didn't multiply yet, because it's possible that when I divide by 100, it will be helpful not to have multiplied. And it happens to be correct. I have a 0 on top and a 0 on bottom I could cancel out. And then I could multiply 13 by 36 and divide by 10. I could also multiply 13 by 3.6 and not have this 0 anymore. So it's completely up to you how you do it. I will choose to multiply 13 by 36. And then dividing by 10 will just move my decimal in one place. So this is 46.8. And if it's a measure of an arc, I'm measuring in degrees. So that's the way I convert 13% for the wrap wedge in the circle graph to 46.8 degrees from the whole 360 degrees in the circle. So if I move on to the second problem, okay, so in the measure of angle FMC, I need to go find F and M and C. So here is point F, and here is point M, and here is point C. And this is creating an angle here. If the vertex is point M, and M is the center of the circle, then we call this a central angle. So I'm finding the measure of a central angle. And in order to do that, I need to do the same thing as I did before. I need to find, in degrees, this big wedge. But this big wedge is going to be given to me in percents. So this portion right here is pop, 9%. This portion right here is country, 10%. And this portion right here is R&B, 11%. So if I add those up, 11 plus 10 plus 9 is 30 for this whole wedge. So this whole wedge is making up 30% of music sales. So I'm going to convert that to degrees. 30% over the whole, so a part over a whole, equals my missing measure of angle FMC in degrees over the whole amount of degrees. And this is an excellent example of why it's best not to multiply before you simplify. Because if I multiply these two together, 100 times the measure of angle FMC, and then I multiply these two together, 30 times 360, then when I do the division by 100, I'm going to notice that this 0 and this 0 will cancel out, and this 0 and this 0 will cancel out. So all I have to do to find my amount of degrees is 36 times 3. So my measure of angle FMC, that central angle measure, is 108 degrees. And that's it. So this problem was about converting, recognizing that the circle graph represents 100%, but also 360 degrees. And it's all about converting that percent to the degrees. So let's go to the next page. So the next part of our notes talks about combining arcs. So the term adjacent arcs means two arcs of the same circle that intersect at exactly one point. And when we talk about intersect, we don't mean cross, we mean share. So the point that they share. That's what intersection means. And so the adjacent arcs that are pictured in this figure would be arc RS and arc ST, because arc RS contains point R, point S, and all the points in between, and arc ST would contain point S, point T, and all the points in between. And this point right here is the intersection. And they only share one point as the intersection, and here it's point S. So it's basically arcs that are pushed together and touching at one point. And so that leads us to the arc addition postulate, which says the measure of an arc formed by two adjacent arcs is the sum of the measure of the two arcs. Now, on the first page, we talked about how arcs were to circles as segments are to lines. And so this arc addition postulate kind of mirrors the segment addition postulate. So here, we could say that the measure of arc RS plus the measure of arc ST is equal to this whole arc from R to T. So the measure of arc RT. That's the arc addition postulate. So we have examples 2A and 2B to help us understand how to use the arc addition postulate. Example 2A says, find the measure of arc CDE. So from C to D to E. I need to find this measurement. So I'm going to put out to the side the measurement of arc CDE equals, and then I'm going to leave it so that I know that's what it is that I'm finding. So there's a couple things that we can notice here. The first is that from CFD, this angle is a right angle. So the arc measurement CD should be how many degrees? Well, since the minor arc's measurement is the same as the central angle's measurement, then CD's measure is also 90 degrees. So now I just need this measure right here. And I notice that I've got 18 degrees over here and nothing over here. But these two angles are vertical angles, and we know from the first semester that vertical angles are congruent to each other. So if the angle here's measure is 18 degrees, just like this one, then I can say that DE's measure is 18 degrees. And by the arc addition postulate, if I add the measure of arc CD and the measure of arc DE, then I should get the measure of the whole arc that I'm looking for, CDE. So 90 degrees plus 18 degrees equals my answer, which is 108 degrees. That's the measure of arc CDE. Oops. Guess I could write it down here in my space that I made for my answer. So let's talk about this one. It asks us for two things. It wants, and I'll write it here because I've got kind of that picture here. So it wants the measure of arc JKL, and it wants the measure of arc LJN. So I'm going to be finding those pieces. Now, there's a lot of stuff going on here. And so what I'd like to do is first mark in any arc measures that I can automatically know what they are. So if this is 25 degrees, then its vertical angle over here must also be 25 degrees. Correct? I also know that I can use semicircles and its property that it has a measurement of 180 degrees to calculate some of these other chunks that I'm missing. For example, if I draw a line KN and I look at arc KJN, so this one down here, the whole arc should measure 180 degrees, but this part's already 25. So what would I have to do to find this leftover part? Well, I kind of use the arc addition postulate and I just reorganize some things, and I would say that 180, that full semicircle's measure, minus 25 degrees equals my measure of arc JN, which would be 155 degrees. So this is 155 degrees. And I could do similar things throughout the problem and draw semicircles to try and get this missing measure. For example, I've already got this line drawn here. I'm missing this piece right here, this arc measure, but I know that this is 40 and this is 25. So together, by the arc addition postulate, this piece right here measures 65 degrees. So if I subtract 180 and 65, then I'll get this missing arc length right here. 180 minus 65 equals 105. Sorry, 115. So that's this arc measure right here, arc KL. So whenever I go find the pieces that I'm asked for, I can just add up all of the arcs that create those arcs that I'm being asked to find. So JKL is right here. So to find the measure of arc JKL, I would add up this arc 25 degrees and this arc 115 degrees, and 25 plus 115 equals 140. So the measure of arc JKL would be 140 degrees. Now when I find the measure of arc LJN, go from L to J to N, I can add up all of those pieces, so 115 and 25 and 155. I could also just do 360 minus 40 and 25. So either of those would give me the right answer. I'm going to go ahead and add up 115 plus 25 plus 155. 115 plus 25 is 140, and 140 plus 155 is 295. So I have a measure of 295 degrees. So now that we're talking about two arcs, we would say that congruent arcs are two arcs that are in the same or congruent circles, and they have the same measure. So not only do they have the same measure, but they have to be in either the same circle or congruent circles. That way they're the same length. So let's talk about some theorems that we can discuss based on congruent arcs. So the first theorem, in a circle or congruent circles, congruent central angles have congruent chords. Remember that a chord is a segment with endpoints on the circle. So here, if I have congruent central angles like angle A or EAD and CAB, notice that they are congruent to each other, then I can say that the chords between those endpoints are also congruent. So ED is congruent to CB. So congruent central angles create congruent chords between them. The next theorem states that congruent chords have congruent arcs. So if I have two chords that are congruent, ED and CB, what that results in is arc ED being congruent to arc CB. So the arcs that those chords create must also be congruent. And then finally, congruent arcs have congruent central angles. So if I have congruent arcs, ED and CB, I can conclude that the central angles of those arcs are also congruent. So angle EAD is congruent to angle CAB. I can conclude those. So let's move to the last page of our notes. Example 3. Applying congruent angles, arcs and chords. If segment RS is congruent to segment TU, I'm going to go ahead and mark that. I'm asked to find the measure of arc RS. So from R to S right here. Well, one of our theorems states that if we have congruent chords, then the arcs that they create are also congruent. So I should be able to set 3x, the measurement of one of those chords, equal to 2x plus 27. I could solve for my value of x and then substitute it to find the length of RS. So I'm going to ask you to pause your video and finish the algebra on this problem. So you should have found that x has a value of 27, and 27 times 3 is 81. So that's the measure of arc RS. In example 3b, it gives us the information that circles B and E are congruent to each other. It also tells us that arc AC and arc DF are also congruent. So we have a theorem that states that if we have circles that are congruent and arcs that are congruent in those circles, well, we can also claim that their central angles are congruent, which is nice because we have 5y plus 5 for one central angle measure and 7y minus 43 for the other central angle measure. So I can set those two equal to each other. And I can solve for y. Once I solve for y, it cut off on the printed version, but this should be the measure of angle DEF. This is what you're finding. So you can take your measurement for y, substitute it, and find the measure of angle DEF. So pause your video and finish the algebra on this problem. So check your work with mine. You should have gotten a y value of 24, and then when substituted into the expression 7y minus 43, you should get an angle measure of 125 degrees. So the last bit of our notes today gives two theorems and examples to apply those theorems. The first theorem says, in a circle, if the radius, or diameter, is perpendicular to a chord. So here I have a radius perpendicular to a chord. I know it's perpendicular because it has this little right angle right here. Then it bisects the chord and its arc. Remember, to bisect means to cut into two congruent parts. So if it bisects the chord, then here's the chord. We'll give this a center point here. So we'll call this point G. We need it to name. So segment EG is congruent to segment GF. And arc ED is congruent to arc DF. So we have a bisected chord and we have a bisected arc. And finally, in a circle, if the perpendicular bisector of a chord, so here's the chord, here's the perpendicular bisector. If the perpendicular bisector of a chord is a radius, the perpendicular bisector of a chord is a radius or a diameter. So my conclusion is that JK is the perpendicular bisector of chord GH. So I'm going to use those theorems in my two examples. So I need to find the length from B to D. So in order to find the length from B to D, I notice that I have this perpendicular piece right here. And I know that in a circle, if the radius is perpendicular to a chord, then it bisects the chord. And it also bisects the arc. Well, I'm not interested in finding an arc measure, but it is nice to know that BC and CD should be congruent to each other. So I'm going to go ahead and give it a measure of x, and if this length is x, then this length must also be x. So it's also worth noting that here we have a radius, and we actually have the measurement for the radius, but it's split up into pieces. So I use the segment addition postulate to find the whole radius length. 2 plus 3 is 5. And we've talked in the past, namely yesterday, about how you can draw a radius from the center of the circle to any point on the circle. And if its length is 5 here, then its length will be 5 here as well. So what you have is a right triangle with a length of 3 and x and 5. And now, in order to find that missing length, you can use Pythagorean Theorem. Or in this case, you can recognize that this is a Pythagorean triple with sides of 3 and 4 and 5. So if x equals 4, and I'm looking for the length from B to D, well, 4 plus 4 is 8. So the length of BD is 8. And finally, in the last problem, I'm asked to find QR. I have this perpendicular chord to the radius, so that tells me that QT is congruent to TR. If this is x, then I can call this x as well. This radius has a length of 10 plus 10, so that's 20. And that means I could also draw it here and get a length of 20. So again, I have this right angle, creating a right triangle with sides of 10 and x and 20. And I could use my Pythagorean theorem to try to calculate this missing side. So I'm going to pause the video, and I'd like for you to finish working out the problem. So if you perform Pythagorean theorem, you'll have that x equals the square root of 300, which can be simplified to 10 square roots of 3. And when you're finding the length from Q to R, you have to add 10 square roots of 3 to 10 square roots of 3, or just multiply it by 2. And the length from Q to R is 20 square roots of 3.